The breeder is a ring. The burner is a line. It's called a tandem mirror, a long, straight column of plasma held between two magnetic corks, and it is where our second machine makes its power. Almost every fusion program in the world burns deuterium and tritium. We do too in the breeder. But the burner runs a harder, cleaner fuel, deuterium and helium-3. When a deuterium nucleus fuses with a helium-3 nucleus, it releases a helium-4 nucleus carrying 3.6 million electron volts and a proton carrying 14.7 million. Both of those products are electrically charged. That's the whole point. In deuterium-tritium fusion, most of the energy leaves as a fast neutron, chargeless, uncatchable, straight into the wall. In deuterium and helium-3, the energy comes out as charged particles you can steer with a magnetic field. We are honest about what low neutron means. Side reactions between deuterium nuclei still produce some neutrons. In our design point, 5.44% of the power. Low neutron, never aneutronic. Anyone who tells you their machine is neutron-free is selling something. But 5.44% instead of 80 means a far gentler machine. Less shielding, less material damage, a longer-lived wall. That single number reshapes the entire engineering problem. There is a price for this fuel, and we'll name it. Deuterium and helium-3 only fuses well at much higher temperatures than deuterium-tritium. The plasma has to run hotter, and hotter plasma radiates more of its own energy away. The way you win that race is to keep the fuel ions hot while letting the electrons run cooler. A hot ion mode. Radiation scales with the electrons, fusion scales with the ions, split them apart, and fusion power stays ahead of the radiated losses. Now, the machine itself. Picture three sections in a line. In the middle is the central cell, a long, uniform column where most of the fuel lives and most of the burning happens. At each end of that column sits a high-field plug, a short, intense magnetic region that pinches the field lines tight and holds the plasma in from the ends. Those plugs are where our strongest magnets go and where the fusion power concentrates most fiercely. Beyond the plugs are the end tanks, large volumes where the field lines fan back open and the escaping particles spread out. Nothing is wasted there. That expansion is the first step of turning the plasma's energy back into electricity. Here is the mechanism that makes a mirror different from a ring. The field lines are open. They don't close on themselves like a donut. The plasma is held not by geometry alone, but by magnetic and electric forces at the ends. Open field lines are the burner's defining feature and its central challenge. A mirror also lets you run at high beta, a large plasma pressure for a given magnetic pressure, which is efficient use of the field you paid so dearly to build. The plugs carry the load. The central cell does the work. When you add it all up, fusion power in the central cell, radiation out, particles lost through the ends, you get the burner's engineering gain. Not a physics curiosity, but the number that decides whether the machine feeds the grid or drains it. And there's one gate standing between this design and an operating machine, a piece of confinement physics called the thermal barrier. We'll cover it in the next film. For now, know that it is a gate, not a closure, a thing to prove, not a wall we've hit. Two housings carry this same physics to two customers. Aegis is fixed defense installations, firm power at the edge of the grid, or off it entirely. MetroVolt sits behind the meter at data centers, feeding the AI boom without waiting years in an interconnection queue. One fuel, one geometry, two markets. This is a conceptual design, validated in open simulation, not yet an operating machine.